So, welcome everybody to the GTV colloquium. It's a great pleasure to have Alok Laddha from CMI, and he's going to tell us about how symmetry constrains gravitation.
Thank you, Lord. And thanks a lot for the whole visit. Actually, I was here for almost a month and I had a fantastic time. So, mostly all of you know me. So, thank you for a very nice month. So, okay, so I will just try to tell you something about some recent things we have learned about gravitational radiation in mostly last decade or so. But the origins of the story go at least 4 or 5 decades back, since the work of Christodolou and Thorne and others. So I will basically give you an overview of some of the recent development in this direction. Okay. So let me just start with some broad motivation. So one of the useful and fascinating quantities that we like to compute in gravitational physics, as I'm sure all of you know, is waveforms emitted during Lagrange spiral or scattering of astrophysical objects like neutron stars, for example. And so this waveform field, if you look at it more quantitatively, is the what leaves of what survives of the gravitational field at very large distance. If your r is the distance from source to a detector, then you basically look at the leading component of the gravitational field, which goes as 1 by r, and then that's the quantity we want to compute in a generic astrophysical process. But as I'm sure most of you know, this quantity is horribly complicated, and it depends on infinity of multiple moments of the radiating source. So all of the details of the source kind of feed into this, which is precisely what makes this very interesting quantity to compute. Because if we know this quantity, then we learn a lot about the astrophysical sources which emit. But however, computing this is of course a nightmare in gravity, because gravity feeds itself. So the more source vibrates, the more gravitational field is produced, which feeds itself and produces more and more radiation. And generally there are broadly four approaches. I mean, if you have access to old Russian books, then you can make a lot of progress. Or there are two expansion schemes, which I will discuss in the next slide. One is what is called a post-Newtonian expansion scheme, which is valid if your sources are moving very, very slowly. So this is the expansion really in the 1 by c, where c is the speed of light, and v is some typical velocity of your source. And there is another expansion scheme which is more familiar to from quantum field theory, which is what is called a post-Minkowskian expansion scheme, which is true if your sources are far apart, so that the gravitational field they produce is weak, and so that we can do some kind of expansion scheme in the Newton's coupling G. And of course, if you don't have recourse to these two, then you have to really do either go to Russian books or do numerical relativity.
So how easy or hard is it to calculate numerical?
Yeah, that is actually I didn't really know anything about that subject, but really what I understand is that for inspiral, for example, now there is a code that runs all the way from the inspiral to the margin, and that was written by Franz Pretorius a few years back. So, so I think numerical relativity is supposed to capture physics of waveforms even during collisions in the last 10 years. But which is where the first two expansion schemes, this one and this one, do not really work.
Just to add to that, for a long time, the problem was that if general relativity works, physics is taken advantage, but numerics is not taken advantage. And for a long time, the problem was that numerics was very poorly reasons, because there was and the big advance that was made 15, 20 years ago.
Yeah.
The people thought, like, hey, this is numerics.
Yeah. Code rate of relativity. So of course, without doing much computation, we can always apply to symmetries to learn something about the radiation. But naively, you would think there are not so many conserved quantities in a gravitational scattering. Because if you take a generic scattering where objects, let's say black holes or neutron star, and suppose they scatter. So let's say we have some n initial astrophysical objects with momenta p1 to pn. So they can be very complex objects, but I'm just assuming that the center of mass momenta in p1 to pn, and then they can scatter, fragment, emerge, etc., into some other objects like stars, with this momenta say pn plus 1 to pn. So of course we know that for the whole system, the total say linear and angular momenta are conserved, and you can compute what's the total linear momentum in the radiation field and the total angular momentum in the radiation field, which is just the, we just have to subtract out the what was the final linear momentum from the initial, and that will be the one that is gone into, for example, the linear momentum of radiation. And so, of course, this is a very well-known fact in classical field theory, and these conservation laws are tied to the fact that even if gravity is dynamical, at very large distance, your space-time is Minkowski. And so, whatever is the symmetry group of Minkowski, which is Poincare symmetry, space-time translations, and Lorentz, they survive as a symmetry. So, all the conserved quantities we have in classical field theory are conserved also here. And so these are the two quantities that we can learn of without in any computation, the gravitational process without doing any computation. But these are not so many quantities, right? So it's just finitely many. So they don't give us so much information about the gravitational radiation that we are interested in computing. So they can serve as a good check, but they don't teach us much. So just to give an example of what kind of monsters we are dealing with, I started a relatively simple example. I mean, these formulas are of course not important, but here's the analysis that Peters did in 78, where he said that let's look at a small, probe particle of mass small n, and which is moving in the Schwarzschild geometry of mass capital N, and so it back reacts on this geometry. So because it has a stress tensor, it is energy, and so it will change the geometry, and so that means it emits radiation. And then he wrote down this kind of integral formulas. They are really like convoluted integral differential equations involving this radiation field that we want to compute. Of course, we can't really solve it analytically. So, but it's a very simple example. We don't have too many black holes or anything. We just have a probe particle in the Schwarzschild geometry, and we are studying radiation, and it's a horrible beast like this. So, even in this case, we see that it's not a tractable computation analytically. If you want to measure what's the radiation field at frequency omega at some angle n hat in the sky. So that's even in the simple case we don't know how to really do it exactly.
So somehow this takes into account the radiation reaction.
Exactly. Yeah. Exactly.
And I'm sorry for great ignorance, but I thought that was sort of hard to do in electrodynamics.
Yeah, it's hard to do in electrodynamics, and it's even harder to do here.
But I hard to do, and then was not in principle. I mean, in principle, what to do was clear.
Yeah, in principle, I would say that in principle, in this case, it's clear in the sense that if you are at a large impact parameter, then you can do a perturbation theory in the impact parameter. So
I see that.
Yeah. So now, just to expand a little bit on the approximation schemes we employ to solve such problems in the gravitational scattering. One is what is called post-Newtonian scheme, and that's a really powerful perturbative scheme which has been developed since 70s, and it applies to gravitating systems like black hole spiral in the initial phase when black holes are far apart and when they're moving slowly. And it's like a little bit similar to people who are familiar with the some effective field theories, for example, the heavy quark effective field theory. And the basic idea here is the following: that you take the gravitational, this radiation field, and you expand it in 1 by c. And so the idea is that can we compute these different coefficients in the 1 by c expansion, like we do in perturbation theory. So that's what this scheme is about. And then another scheme which is called post-Minkowski scheme, which is also rather popular, and it's very close to how we do quantum computation in quantum field theory. So this scheme applies to the gravitational objects which are scattering, emitting radiation, gravitating objects which are scattering, emitting radiation, which are quite far apart. So they don't interact very strongly with gravity, but they can be moved with very high velocities, like unbound orbits, for example. So in this case, this scheme will not apply because the velocities of the particles which are scattering are not Newtonian, but you still have expansion in the Newton's constant. So it's very similar to perturbative expansion quantum field theory, and this is schematically the expansion scheme. So you do expansion in gravity. So the main point is that in both these schemes, what we learn is that they are constrained from the sources that we are which are radiating. So here the sources are moving slowly. Here the sources are producing weak gravitational fields. So we can ask a sort of a little different question that can we develop a scheme where we constrain the detector rather than the source? So in the following sentence, suppose we said that okay, I want to place a detector at far apart at infinity, whose frequency band is in the infrared. So the frequency that the detector is sensitive to is much smaller than any characteristic frequency that the system has, for example. And so the radiation that will be measured by the detector will only be the infrared radiation, and typically this is what's called soft radiation. So in this case, the perturbation parameter is the frequency range of the detector divided by the characteristic frequency. So we are really not, but we are not saying anything about this as characteristic. It can be anything. We just want this parameter to be small, which is obtained by basically constraining the detector. So it's morally a very orthogonal scheme than what we the post-Newtonian and post-Minkowskian. And so that's where the advantage also in principle lies, that if you are interested in computing soft radiation, you don't have to constrain your sources. They can be anything. So if you try to develop this scheme, so this is the scheme that we will explore in this talk. It's really what is usually called the soft regime of gravitational radiation. And I'm just giving you a schematic expansion of this, and then we'll try to see how some of these coefficients can be computed exactly, no matter how complicated your scattering is. So this is what this expansion in omega, and so this is schematically I've written down this soft expansion. I'm looking a little bit ahead of course, because you can ask how do I know that I have coefficients like this. We will see why this kind of coefficients come later. But in general, I just want to remember that it's expansion in small omega. And so that, of course, you could ask what's the big deal. I mean, I could set up this scheme and then do computation, and then it would be as hard as doing other schemes, for example, post-Newtonian and post-Minkowskian. But the whole point is that we will see that the set of coefficients in expansion actually have analytic formula, not all the coefficients, but a subset of coefficients, which are fixed solely by asymptotic. So, for example, the asymptotic moment of your scattering objects, or the angular momentum of the scattering objects. And so those coefficients are really theorems in the sense that they can be computed just to the initial and final momenta and angular momenta of the black holes, but you don't need to know anything about how the black holes scattered or joined. And so if we could come up with this kind of formula, of course they are interesting because they apply to all processes in general. And so that's the main motivation of looking at this expansion. So just to give a parallel that this is not something unique to gravity. You could do this also for electromagnetic scattering, as Shiraz was asking. So then we could look at the transverse component of the gauge field, which contains the information about the radiation at frequency omega and direction and hat. And again, we could ask the question that could I, for a generic electromagnetic scattering, do this kind of expansion by constraining the detector? And so something similar. Although we will not really go into details, that many of the coefficients are fixed just by the asymptotics of the scattering particles and do not depend on what the details of your equation of motion are. And these are typically called soft photon theories. So there's an exact parallel to what I want to talk about in electromagnetic theory. So just to give some motivation. So the formula which was produced by this soft theorem, which is some coefficients in this omega expansion, they are very similar to, they are very similar to computation of total angular or linear momentum in the radiated field, in the sense that, as we saw that total linear momentum in the gravitational field is computed by just the asymptotics of the scattering objects. So if I know momentum of all the objects, then I know what was the momentum lost. And since the soft theorems are also obtained, as you will see, only from the asymptotics, there's an actual question to ask if soft theorems are also tied to some symmetry. Just like the linear momentum of the gravitational field is tied to the space-time translation symmetry. And it turns out that this is indeed true, and especially over the last decade or so, we are beginning to understand that these soft theorems, the coefficients that we can compute without knowing the equation of motion, they are also actually just conservation laws in secret, and they are tied to very rich infinite dimensional symmetry structure of classical general theory. So at least little bit. So we will try to explore at least some connection between these symmetries. These are called, for historic reasons, asymptotic symmetries, and this classical soft theorem, and how they inform each other in the sense that they can feed on to each other. Once we learn more about soft theorems, we learn more about symmetries and vice versa. And in fact, once of course, if you have symmetries for classical scattering, then you could ask if they are unbroken in quantum theory, and they indeed lead to some interesting infra-red constraints in quantum gravity. Although I will not be able to do this detail.
Are there any other implications of this symmetry apart from this? The top?
In the classical theory?
Yeah.
No, there is none.
Okay.
Yeah.
So this is the review.
Yeah, it's very formulation. So I don't think in classical theory, to my knowledge, it offers any advantage at all. If you know soft theorem, you know symmetry. The question is that once you have this symmetry, then can they use spinning quantum?
Right.
Yeah, please. Thank you. Similar to what people do in adiabatic perturbation theory, where you consider with the dynamic with very low computer characteristics scales of the system.
But here the dynamics cannot be adiabatic, so it can be like in collision. The frequency is the frequency the detector is measuring. Sensitivity. So
I see. The radiation actually emitted
yeah, it can be. Yeah. Of course, you are right that if it was adiabatic, then the dominant contribution will be in the soft regime, and then it will be enough to know the software. But in general, of course, this is a very little information. Yeah, that's an important one here. Okay, so let me give you some early. I mean, these ideas are not new, although they are kind of now sort of repackaged in the sense as Shira said. But really, the first hints of the soft theorem go to 60s. Where Zeldovich, Polnareff, and also independently Braginsky and Thorne analyzed zero frequency limit of gravitational radiation, which was emitted by particles which are propagating in Minkowski spacetime. So you have like a weak field limit again, your particles scattered in Minkowski spacetime, but interacting gravitationally, and then you want to see what gravitational radiation is emitted. And so their conclusion was in the context of weak field approximation, but in 92, and they had some nice formula where they showed that this, we will see the formula in detail here, but the formulas were kind of exact for any kind of scattering of particles. But Christodolou proved in 92 that the result was actually a special case of an analytic result in full general theory of relativity. And so this is the result that Christodolou proved, which is an exact result in general theory. So, so this is the point is that if you look at the soft expansion of the radiation field, then Christodolou proved that the first term that you get is which goes as 1 by omega. There is no term lower than 1 by omega. And this term has the following form. So if you have some, these PIs are momentum of the scattering particles that you have in the game, and that is the direction at which you are evaluating at which your detector is sitting in the sky. And so you have a contribution from the scattering particles, but also exactly as Ranjiv said, you can have in general appreciable gravitational radiation emitted, appreciable gravitational momentum emitted in finite frequency radiation. So that also feeds into this zero frequency component. So this is the result that so this P mu n prime is the linear gravitational momentum which is radiated at some solid angle n prime that we have to integrate. But one can show that, as Mr. Bloom, that this has contribution only from finite frequency. So this formula is not an identity. It's really a formula where you get the zero frequency guy from the finite frequency component and the momentum of the scatter. So this is really the first interesting result that one obtained in this expansion, where one got because this you could have any scattering process and this result would not change. And of course, this has actually a parallel in electrodynamics, which is in actually Jackson, where he shows that if you again look at zero frequency limit of electromagnetic radiation, where you have charged particles which scatter. And then this is the formula that you get where capital squares are the charges. P's are somewhere, so I have been schematic here. This is somewhere incoming as well as outgoing momentum. Be careful with the signs and all, but this is the result. This is exactly the same sort of result that I should have written. I apologize. I should have written Jackson here. Yeah. Okay, so that was one first evidence that when we get the soft regime of gravitational radiation, we get some analytic formula. And in fact, there was a parallel development that happened in general theory in 60s, although completely divorced from the Christodolou development from memory formula we talked about. So here, basically the idea was that people like Penrose, Bondi, and others, they wanted to see what is the class of spacetimes we get when you have gravitational radiation. So the first thing you notice is that if you have a source which is radiating, then of course the radiation is going to peel off or die down at large distances, at some power in one balance. So this power can vary depending on what your source is, but of course it will die down if your source is, just compact and not spread all over space-time. So that at very large distance, space-time becomes Minkowski space. So this is of course an intuition that they wanted to build on. And you notice that because gravitational radiation is massless, it always travels in what we call null directions. So so that decay is also in null direction, and so the emergence of flat space-time as you move towards infinity is also in null direction. So if you move in null direction, you see that the space-time becomes flatter and flatter. And the boundary that you reach as you move in null direction is what is called null infinity. And so these spacetimes which are such that they become Minkowski as you move in, in light rate direction, they are called asymptotically flat spacetimes. I mean, it's just some jargon. And so there are two null infinities, as you can see. One where your light ray emission, the light ray will end. One where the light ray will begin. If you observe a light ray which came from past, there it began from. And both of these are, as Penrose and others showed, they are both cylinders. So they have a cross section which is a sphere, and they have a sort of a null direction, which is kind of like time direction for this. So these two infinities in the past and future, that's the boundaries of space-time. They are pronounced as chi, and they are denoted as chi plus minus. Plus minus go for future and past, and they are topologically S2 cross R. So for purpose of our talk, we will denote the S2 coordinate standard, like standard as theta phi, and this R could be labeled by is labeled by U if you are in the future null infinity, because that's where your outgoing null lines end up. So if you move radially outwards forward in time, then the parameter that doesn't change it will be the U coordinate. It's called a retarded coordinate, and all the incoming null lines will be labeled by V, which is usually called advanced coordinate. So that's the coordinates on your boundary. And because the metric is flat at infinity, the metric on the sphere is really the standard sphere metric. So nothing really happens. So if you're in flat space-time, just flat space-time with no radiation, then you just have these two boundaries, and then there's this boring metric sitting on the sphere. And now you can ask, and this is what Bondi and others asked also, like what happens to this metric at infinity when gravitational waves arrive? And what they showed just by analyzing Einstein equation is that it disturbs the metric, but at 1/2, not at the leading order, but at 1/r in the larger expansion. And so the metric, which was flat to begin with, remained flat at leading order in R, but then there's a small deformation, 1/r order. And just to give a parallel with the electrodynamics, the CAP is very analogous to the transverse component of the radiative gauge field. So which falls off as 1/r, which is components moving in 3 times 5 direction. And so just keep that as an analogy here. And CAP is kind of the star of the show in some sense if you are interested in studying solution to Einstein equation, because it's a free data for the vacuum Einstein equation. So you specify the C at scribe plus or scribe minus, then you can solve Einstein equation, at least vacuum Einstein equation, and then get metric everywhere. So you could have a non-trivial metric inside space-time, even without matter, if you start with some gravitational waves at infinity. Okay, so now once you kind of formulate your dynamics in this way for gravitational waves, you realize that you naturally kind of get more symmetry in your theory than what you would have anticipated. So naively you would have thought, okay, space-time is flat at large distance, so that means that the symmetries are just point correct. In particular, your space-time translation, there is symmetry, and in some small algebra that shows you that if you see how space-time translation acts on this coordinate view at null infinity, then time translation just shifts you, which is kind of expected. And there are 3 space-time translations which kind of change you by some, this first spherical. Okay, so this is just an algebra that you get just from looking at how T and R transform to how to transform. Because remember, U is T minus R. And so that's why U is also sensitive to space translation. So this Bondi Martinez have realized that there is an obvious tempting generalization of this symmetry, which is that why not you try to change U by a generic function of theta and phi? Why not operate line? But of course, I would have thought that if I do this, then my space-time will not remain flat at infinity. Because the flat space-time only has this as my as my space-time translation rule. But what BMS showed was sorry. So what BMS showed was that I think the battery. Okay, so the what? I think
I mean the arrow if you want.
Yeah, I just wanted for the pointer. So yeah. So what basically BMS showed that if you do this transformation for a generic F, then you're this.
Sorry, I meant just when you go back and forth.
So but yeah, okay, that's it. So then the sphere field scheme, which contains information about gravitational data that transforms to non-trivial level. And again, you can draw parallel with electrodynamics, where there are, if you take gauge potential, then you can always do a gauge transformation, which does not die down in larger, as I have written there in that red formula there. So in electrodynamics, these are for large gauge transformations which don't die down in larger. Super translations are exactly same. They are transformations of space-time which do not die down even if you put to infinity. And so it was realized in 60s that there are these infinitely many, but F can be any function, so you have infinite dimensional symmetry of your theory, general theory of relativity. But it was not known that no one initially it was not appreciated these symmetries have anything with this memory formula that we talked, we saw earlier. In fact, people were interested in this symmetry to generate new solutions to Einstein equation. So you start with one solution like Minkowski, you do super translation, and you see what kind of space-time you get. But it was not appreciated that they would constrain scattering in any way.
Sorry, so Minkowski and these two, what way that you get?
Yeah, so which is also flat, but it's a flat space-time in which the Lorentz group you cannot canonically identify with the Lorentz group that you started with. So what that you have infinite many flat space-time, but they all differ by coordinate transformation at infinity. So yeah, so
Can I think of that as
yeah.
Yes, there's other things that are different ways of cutting off the same flat space. That's right.
No, so one way to probe them will be that if you compute like angular momentum density of the different spacetimes. So to begin with, Minkowski has no angular momentum. Now you do the super translation, you see that it has some non-trivial angular momentum.
I see. And this is a measure of the thing you would be able to present.
But they are all flat, so it's only relative. So it's related to the fact that you cannot identify the Lorentz group between two of them. But it's really related.
Okay.
Yeah. But I think you're right. You could declare any one of them to be flat, and then you would not within a spectrum you cannot measure the effect of supertrons. I think that's what you're asking, right?
I was thinking EDS3 birds.
Yeah.
We have these large scale transformations.
Yeah.
One way of thinking of them is that one God given the EDS3 that you cut it off.
Yes.
Different cutoffs that produce these different.
Yes. Yes. Yes.
The one thing that was some similar.
Yeah. So these are large scale, not in the sense of they are still connected to identity.
Okay.
So they don't change the topology.
No, it's even an area.
I see. So you are not talking about the large scale.
No,
I see.
I mean the boundary parameters.
Yeah, these are similar there. These are the ones that will induce. But yeah, I think let me see. So boundary gravitons also zero frequency gravitons in some sense, right? Because they just live at the.
They live all the way at the boundary. And one way of thinking of them is, I got my same area space, I put a cutoff.
Yeah.
Now I do a quantum transformation.
Yeah.
That changes my cutoff. So
yes.
If I don't change my cutoff,
yes.
In the new quantums I have the same cutoff, that's now a different way.
Yes.
Because it was a different way.
Yes.
Or the dating value, right?
Yeah.
Dating value.
I understand. It's exactly this.
Okay.
Yeah. So now what I want to argue is that if you these new symmetries give rise to interesting conservation laws for classical scattering, and we will see that those conservation laws are precisely the memory formula that we derive. So let me just give you some prelude in electrodynamics first.
Does that mean there are some dynamical modes?
Yeah, they are. Yeah. So if you do a super translation, then you so if you start with Minkowski, which has no dynamical modes, you do a super translation, then you induce a like a zero frequency component of the gravitational.
There's an effective action for these modes.
Yeah, you can actually this has been done only in 3D, where Karlik wrote down you start with 3D Minkowski and you do a super translation, and there's a Schwarzian action you can write down on that. So yeah, it's very simple. Yeah. So the usual symmetry of Maxwell's equation, we can of course use our standard, electric charge, which is take the sphere at infinity and compute the integral of the radial electric field. And so there is an exact parallel of this in general theory of relativity for usual spacetime translation. So we know that, because spacetime is flat at large distances, we have the spacetime translation of symmetry. And you can, what are the charges for these translations? And they can be computed in a very similar way, where basically the idea is that there is an analog of the electric field, which is called a mass density, as you kind of expect in gravity. And that mass density is, it's a function of theta and phi. It's a mass that we evaluate at large distance, and you integrate it with respect to this global translation. So either constant function or one of the 1Ms, and then you get either total energy or linear momentum. So now we can ask, okay, so these are the global charges for translation. So if I, instead of this global translation, if I look at a generic super translation, generic function F, then we will get some charges, right? Because this is just substitute for F, we can compute. And now we can ask, are these charges conserved in gravitational scattering? So if my F was one of these, then of course we know that these charges conserved in scattering because it's just total linear and angular momentum. But if not at all, obviously, if I take a general random F, then it will be conserved. And in 2013, Schrödinger proposed, and in fact later with Prahan and Lysov proved that at least for a class of scattering processes, all of the super translation charges are conserved. So this was, I would say, quite a remarkable result. That you choose any F, and they showed that for a certain class of scattering processes, these charges were exactly conserved in the past and future. Even though they initially looked at a very specific class of processes, their proposal was later turned into a theorem, really, in the sense that for any classical gravitational processes involving arbitrary sources, one can now prove that these charges are exactly conserved within the past and future. And so that's a long list of authors that I haven't had time to put everyone's name. And so now let me write down what is the implication of this conservation law. So this is the statement of the conservation law, that I take any of these function F, I evaluate the charge in the future. So at future null infinity, in the past, and this exactly equal. And now if you write this down in terms of a gravitational field data, then you see that this is the result that you get. So if you just write this down in terms of your all the sources you have, all the field at infinity, then this is the result. So what you see is that the gravitational field at in the far future minus the past of future null infinity is related to the similar quantity in the past null infinity by this stuff here. So if you remember, this is exactly the Christodolou formula that we had. And so now if you demand that, and if you go to Fourier space, then this quantity is simply this guy. It's just a zero frequency component of the E. And so if you have no incoming zero frequency radiation, if you demand that this quantity is zero, which is reasonable thing to do that, because you are starting fast from a system, then you precisely recover the Christodolou formula. So it shows you that the memory formula you derived really is a theorem because it's coming from a conservation law, just like in the case of total linear momentum. And the fact that we have infinitely many F basically transmutes into the fact that the Christodolou formula is for any direction n. So we just played this F with the direction of this F. So infinitely many memory formula come from infinitely many conditions. Okay, so now, we could, little bit get excited and ask that, okay, so super translations, so far we only looked at super translation which enhance the global translations to some infinite dimensional group. But we could ask the following question now, that, the full symmetry group of general relativity at infinity was not just translation to begin with, but translation as well as Lorentz group. And obviously, it is this group that ensures that the total angular momentum is conserved in any scattering process. And okay, there's some small technicality, not very important, but if you think of this group at scribe plus or scribe minus, then it is what is called a global conformal group on the sphere. And you can again rewrite the total conservation law for angular momentum in terms of data at infinity, which is this. The details are not important, but this is really, it's very similar to the equation that I wrote for the linear momentum, which was this equation, where m is mass density, and similarly there is something called angular momentum density that we get in GR. And now if you have any of the global conformal field, then the total angular momentum conservation law is this thing. This is just some kind of a fancy way to write that total angular momentum is conserved. But once we have this equation, we can stare at it and ask, okay, why would be arbitrary vector field on the sphere? Is that possible? And so it turns out that, but before asking that question, we have to ask, if I take an arbitrary vector field, does it preserve asymptotic flatness? Because it's not at all obvious that if I enhance this Lorentz group to a random group of transformation on a sphere, why should the metric at large distance remain flat? And so it turns out that at least this is something we have nicely understood in last 10 years or so, that even if you take arbitrary vector fields, they generate symmetries which preserve asymptotically asymptotic flatness at infinite distance. And again, this is what the transformation is of this arbitrary vector field on the metric at infinity. So in the case of super transformation, we saw that the transformation, sorry, if I go back a little bit, was this one. So if you notice, it did not change the metric at leading order, but it only corrected the metric at next order in 1 by r. So it did not change this QFB metric. But what these vector fields now do is also change the QFB metric, because they are just generating smooth transformations on the sphere. But so nicely you may be worried that if it does this, maybe it doesn't preserve asymptotic flatness, but you can actually check that it does. And okay, so once we have this, then we can ask, what if I look at the global angular momentum conservation law, but replace this global conformal field with generic fields here? So then this will be our conservation law. And then we can ask if this is true or not in scattering. So it turns out that we can first, let's try to do the following. Let's try to write this conservation law in terms of the fields at infinity, exactly as I did for the memory. And this conservation law takes the following form. The form is that what it computes is the omega to the 0 component of your radiation field in terms of the asymptotic momenta and J, the angular momentum, the scattering particles, and the linear momentum of the gravitational field and the angular momentum of the gravitation. So this formula is very, very similar to Christodolou formula, except that it also depends on the angular momentum of the scattering. So the fact that if we ask that, if we postulate, for example, that can this be a conservation law for a gravitational scattering, then this is the answer we get, which trims down one of the coefficients in the soft expansion of the radiation. So that's an interesting, if you want to propose that, the conservation law associated with this new symmetry fixes the omega to the 0 component, and okay, this is called subleading subgraviton theorem because the leading term was 1 by omega. But okay, we can ask, are these conservation laws true in generic gravitational scattering? Because it's something that we have sort of postulated by asking that, we have postulated this conservation law and then we have derived this fact, but we don't know if they are really true. So there are some certainties that we immediately start seeing in 4 dimensions. So let me first expand on them. So by the way, sorry, I forgot to mention that as I wrote here, this quantity is called the spin memory because of the fact that it depends on the spin also of the SU. So before we can ask whether these are conserved or not, we really notice something, that these are actually problematically defined in 4 dimensions, because they depend on asymptotic angular momentum of scattering particles. But these are certain things to define in 4 dimensions for the following reason. That if I consider asymptotic trajectory of any particle which is gravitating, then because of this 1 by r effect, it has a logarithmic tail term in the trajectory, as you can immediately check. This is nothing to do with GR, this is also true in Newtonian dynamics. And this is specifically, this is tied specifically to d equal to 4. And actually, I don't have much time to get into this, but it's also tied to the fact that asymmetrics is higher infra-divergent in 4 dimensions. But what this causes a problem in our spin memory formula, because of the fact that if you now compute the angular momentum of any particle in the past or the future, so plus and minus is always a past and the future term. But if I just compute this, you can check that this will diverge because x is a log term. So this whole thing will diverge. This t will never diverge because we have p wedge with p is of course 0. That is why if I did not have this term, my asymptotic angular momentum is well defined. But this term makes this angular momentum diverge in the past and the future. And so in fact we can write down the formula, we can write down a formula which looks like this. And if I substitute this quantity now in my spin memory formula, then I have this kind of a divergence term. I just substituted the initial and final angular momentum in the formula. And this looks a bit strange formula because we were supposed to be computing frequency expansion of my radiation field, and then we end up with some time dependent. So with Ashok, we made an educated guess that okay, maybe this formula really is telling us that there is a log omega term here. So because t is a late time and omega is a soft frequency, we could make a guess that let's replace log with log omega inverse, and then we will get a coefficient. We will get a term for the radiation which doesn't go as omega to 0 but as log omega. And so this gave us, so based on this, we proposed that there was possibly a spin memory related term in 4 dimensions, but it did not go as omega to the 0, but as log omega. But at this point, it was a proposal. We did not have a proof for this. And in fact, there is a certainty here that I just quickly mentioned that if you now, so far I have only looked at the gravitational radiation which is emitted by the particles here, which is this log term here. But if you include this nonlinear collections in general theory, then any outgoing gravitational radiation will also feel long-range effects on the background radiation. So there is a Coulombic gravitational field which also slow down the gravitational waves which are emitted. And so this basically gives rise to a phase lag in the gravitational radiation. Which basically gives you a further contribution which goes as log omega. So the details are not important, but basically the idea is that if you have a scatter like a source, like a black hole of mass 10, and you have a probe particle which is scattering and emitting radiation, then you get this kind of further log contribution in addition to this contribution that we have. So there are two sources of log that we get, one from the educated guess from the spin memory formula, and one from the looking at the retardation effect of the of the Coulombic mode on the radiation. And now these are proposals. We have got, this is not proof right now, but we can test it in a variety of examples. And in fact, the nicest one that we tested was this ugly formula showed by Peter earlier. So we took this integral formula of Peter and we did a small omega expansion. And we saw that the 1 by omega term produced Christodolou memory, and the next term was a log term which precisely matched with this result here that we had proposed. So, so it kind of confirmed that our formula was we were probably on the right track. So now let me write down all the coefficients we have found so far, thanks to asymptotic symmetry and some educated guesses. So we have the memory formula that we had from decades back by Zeldovich and others. And then we first found the fact that we have this extra symmetry, new symmetry that we have discovered in general theory. They gave us some formula for omega to the 0 component. But we saw that that formula doesn't quite work nicely in 4 dimensions because of this long range effect, and it induced this further coefficient. It gave us this coefficient. So we can now ask, okay, when is this a good observable? Because it seems like it's always dominated by this log term. And it of course will be a good observable if you can ignore the late time tail. So for example, people who study in-spiral problems, where you start from in-spiral, so there is no at initial time you have stationarity in the far past, your particles are not going log or anything. Then for in the in-spiral, this is considered to be a good observable. And it's been computed by people who do post-Newtonian expansion, etc. But otherwise, in a generic scattering, you always get this term which dominates this spin memory. You may be very worried that these are all proposals, random proposals at this point, but in fact, you can derive this theorem from first principle without using any symmetries and simply using equations of motion of classical theory. And in a really remarkable paper, Ashok, Vishwajit and Arnab, they derived this formula for a generic classical scattering in 4 dimensions. And if you assume stationarity in the, if you assume the Coulomb tracker is not, then we showed that there is a spin memory formula which is also used. So it just comes from analyzing equations of motion. So Abhijit, how much time I have? Okay. So I will just now, so the spin memory inspired tail term has some nice consequences. So maybe I just give you some interesting sort of semi-observational consequences. So let me first assume. So now I'm going to work with, instead of E mu, I'm going to work with only the spatial components, because you can always go to this traceless transverse gauge and just focus on the 2 polarizations of the gravitational radiation. And so, and let's assume that at early times, and as you goes to minus infinity, there is no radiation, which is a reasonable thing to assume in a general, like say in spiral, for example. And then this, the formulae or spin formula or soft expansion produced for us. The following, the first 2 terms are the memory term and the term imposes log omega at small omega, and you can check that the Fourier transform of log omega at small omega is 1 by u at large nu. So this is the formula you have got when you are looking at the radiation as a function of u. So u is the time. So you have a detector which is sitting at some time u and measuring the radiation in the direction n hat. And this is the first two terms that detector is going to be sensitive. If your u is very, very late, so you start your detector at very late times, at the end of the universe in some sense. And so let me give you one example here. So let's assume a specific example where the recoil is very, very small. So you have a particle with black hole of mass m. It just emits a lot of radiation, but the radiation it emits is much less compared to its mass. So the loss of mass of the black hole is, for example, very, very small. So this is the kind of thing that we are considering. We have a system of cap m, which fragments into m prime and a bunch of tiny particles, mi. But mi are very the net sum mass loss in mi is very small. Then you can easily evaluate this formula that we had here, and you can they take this very nice form. These betas are just velocities of these particles with mass mi, and this is the exact formula you get for this 1 by u contribution, which tail term. And it turns out that this formula was actually independently derived by Christodolou long back. If you assume these velocities are non-relativistic, you get an even simpler formula, and that was derived by Christodolou long back. And his motivation was to show that if you start with the spacetime which is flat in the past, then it will never remain flat in the future, in the sense that, so this is a little technical, but this idea that General Relativity had that gravitational waves should follow at a certain rate, that rate is violated as long as this term is non-zero. So this particular mathematical property was called peeling, and Christodolou showed that as soon as you have terms like this in radiation, your spacetime do not remain, do not satisfy the criteria Penrose and others had in the future. So therefore, this has some interesting consequences for analytic GR also. So okay, just some further consequences of this tail term. So this is the tail to the memory in the sense that it's, if you have a detector at very late time, then it's the term that decays as 1 by u. And so in the end, this tail dies down, and all you're left with at infinity u is the displacement memory. So it really computes the rate at which the linear displacement memory builds up, Christodolou memory builds up. And this is a kind of a fact which is remarkable that we observe and we don't understand its reason, that if all the energy is carried away only by massless particles, so in the sense that if you look at this formula, and if you take all the betas to be 1, all your particles are massless, then it turns out that the state term exactly vanishes. It's not like small, it's just exactly 0. So there are cancellations between different terms and they exactly give you 0. And the origin of this cancellation is still not understood. The fact that it's exactly vanishing tells us like that and because we don't like fine tuning, that there must be a symmetric reason for this.
So when you say observe, you mean proved or?
Yeah, in this example it's observed, but then in the later papers Ashok and Vishwa proved that this is a generic case, that if all the outgoing particles are massless, then there's a cancellation. So I should have written more carefully. So that and in fact, in some sense, the tail to the memory is simpler because it has no contribution from finite energy gravitational radiation. So remember that the memory there was this Christodolou term, which is complicated, but tail only gets contribution from massive particles because of this result, this quoting here. So you have no contribution from finite energy gravitational fields in the tail. So it's actually easier to come. Okay, so let me just conclude that these classical theorems offer an interesting class of non-perturbative formulas of waveform. Non-perturbative in the sense we don't do perturbation in 1 by C or G. You can have position, you can have any kind of hard scattering, and this formula will still remain valid. And it gives you formulas for waveform which is measured by detector at very late times. And we saw to some level that they are intricately tied to infinite dimensional symmetric group in classical GR, whose first two stages we understand very well now. There are these super translations that DMS discovered long back, and this diffeomorphisms of the sphere. But it turns out that as we find more and more coefficients in the soft expansion which are universal, more and more symmetries are being explored also, which must be responsible for considering these higher order terms, which I didn't have time to talk about. And which Sayali here has worked on many of these higher order universal terms. And although the way we discussed log tail, it was we kind of motivated it from the spin memory, it should be really, it's absolutely not clear what is the relationship between this tail term, which dominates at that time, and this new symmetry that we have found. We have not been able to show that these terms are actually result of this conservation loss coming from the symmetry, because this conservation loss gives us the omega to the zero terms. And in fact, okay, this is another thing that I did not talk about, and this is Shira's first question, that these are, in fact, these soft theorems are classical limit of certain factorization theorems of amplitudes in quantum gravity, and they offer an intriguing perspective on infrastructure of quantum gravity, in particular string theory. So Alok can derive these theorems for string amplitudes as well, and theorems, their classical limit gives us these classical soft theorems. And okay, finally, I just want to thank all my collaborators and friends, and because everything I say here, I learned from this. Yeah, thank you.
Any questions from the Zoom audience? Okay, any questions from the audience? Okay, so your talk was extremely clear.